Hello there. So you may have been looking at some of my videos in the past, especially ones on Simulink, which seems to be very popular with master's students across the world. Had some very interesting emails, mostly telling me that something doesn't work from the far-flung corners of Brazil most recently, which was quite nice. It does work, by the way. The model, you need the right version of Simulink. So let's talk a little bit about something different, because I've been doing a lot of circuit type stuff, which is my usual stomping ground. Mostly is instrumentation, power electronics, electro-optics, that sort of thing, and embedded systems as well. But the embedded systems tends to be more to solve a specific problem for somebody when money's at stake, so it doesn't end up going on YouTube. There are plenty of YouTube videos about embedded systems anyway. So I think this time I want to do a few videos on finite element analysis, and I'm going to choose to do it in Elmer, which almost nobody has ever heard of, which is a crying shame because it's a really versatile simulator. It's been described as the COMSOL open source. It's nothing to do with COMSOL, but it is open source. Has been since about 2005. So it can solve problems in electromagnetism, in structural mechanics, in fluid mechanics. It can solve problems in the flow of ions through porous media. So if you like batteries, that's a pretty good starting point. It can solve problems to do with compressible and incompressible flow, all sorts of things, much more than I am competent to discuss. The workflow is, as is often the case with open source software, a little bit convoluted, and that creates a barrier to entry for many people, especially if you're in a hurry. So if you've got 40 grand available and you fancy doing it in ANSYS, then by all means do that. If, like me, you tend not to do a very great deal of finite element analysis, but you need it for certain specific things now and then, you can rent one of the big packages, and that's commensurately expensive, or you can learn to do it in something which is free, because ultimately it's solving the same equations using the same methods. The only difference is you have to know how to talk to the simulator, and that can take some time, so you have to invest a bit of time in learning it. And to make that easier, people put videos on platforms like YouTube, so hopefully some people, probably students, must be because the students always, they get their problem from their professor for their thesis, and the first thing they do is Google it. Maybe I'll rank high on Google, that'd be quite nice. So we'll try and have a look at the workflow for a 2D electromagnetics problem in Elmer. And this will be a series of videos. I don't really know how many, because I'm kind of making it up as I go along. Don't have a lot of time to sit and write these things and make them pretty. They just are. It might be 4 or 5 videos. But what we'll do is we look at the workflow is you create a geometry, then you mesh it, then you apply boundary conditions and materials, and you apply the external stimulus, which Elmer calls a body force, which is perhaps a little obtuse. And then you solve it, and then you need to use a program to view the solution and decide if you've screwed it up and it's invalid, or make use of it. If you can, you want to do some more post-processing, maybe in MATLAB or in Origin or something like that, Octave maybe. So that's the overall scheme. So it's the same as if you do it in ANSYS or COMSOL or Flux or JMAG or Vector Field or blah 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 blah, all the others. Sorry if I missed if you work for one of the simulation companies and I missed you, I'm very sorry, I didn't mean it. It's not personal. There are other open source simulation tools. There's quite a lot of finite difference time domain tools available. They're quite quick to write usually, maybe only a couple of hundred lines. They're very good for simulating things like antennas, because you don't actually have to mesh the space between the antenna itself and the far field, because of the way the simulation works, or the way that the solution is constructed, which can make it very quick. However, they don't deal very well with differing materials, especially different materials within the same object. Also because of the way the problem is constructed. And for that reason, finite element method has become relatively ubiquitous. There are others like finite volume method, which are also very popular, but the principal one, I think, is finite element is the most well used, shall we say. So the main competitor for Elmer is probably OpenFOAM, OPENFOAM. I've never used it, not out of prejudice. I fell into Elmer and I liked it and I haven't left it, which is great. As I understand it, the workflow for OpenFOAM is very similar to the workflow for Elmer, and in fact you can couple the two together should you need to. So you can get on Google if you want to look at your options in that regard. Righty, so we'll have a look at the overall scheme, and then probably in another video we will do geometry, and in another video we will do the meshing, and in another video we will deal with the solution, and probably look at the result as well. Because we're only doing it in 2D, it's actually quite easy to see if you got it wrong or not. When you are starting out in finite element analysis, it's better to compose the simplest possible problem that you can, even if it's to the point of being trivial, and then add bits to it, including adding an extra dimension if you need to, in order that you can validate your result by comparing it with a solution that you can compose analytically on a bit of paper or in MathCAD or whatever, and that you know your simulation's okay, because if you put rubbish in, surely rubbish will come out just the same as spice. Okay, I think that's more or less it. So where to get the software is the next question. Now you've had a good old, oh that was weird, wasn't it? Let's do that with something else. Great fun, it goes on forever. If I was Keanu Reeves, now I'd say guns. Just guns would. Anyway, let's not do that. Right, get rid of that one. This one. Whoops, this one. So, Elmer, you can get it from here, elmerfem.org. If you type that, it just pushes you to /blog. You don't have to compile it, although if you're feeling brave, you can compile it. I have compiled it for Debian in the past. If you go that way, make sure to compile in the Open Cascade aspect, otherwise it will be quite difficult to open CAD geometries from CAD programs like Creo or SolidWorks or CATIA or Autodesk, and it will make it rather troublesome to use. As it is, I'm going to show a method where you don't have to import from CAD. I may later do a CAD import one as well, but I thought I'd show it with only open source tools. Although you can use Freecad, which is very good for 3D parametric drawing, and is open source as well. So you can get it as a virtual machine, and you can get it for Windows. If you do pull the virtual machine, it's about 6 gigabytes. It's Linux Mint, but it has everything in and it's all compiled and it just works. It's great. And they are relatively up to date. If you look at the moment, oops, apparently it's Ubuntu. It used to be Linux Mint. What's the date on that? 2020-07-25, and the date today is the 18th of August. August, so it's about 3 weeks old. So it's compiled pretty regularly, and that's not an unusual length of time for it to have it to be sat there. So there will be another one before too long. You can of course pull it for Windows if you want it for Windows. It says AMD 64, but actually it will run. This is to do with the instruction set, not to do with the processor type. So you can run it on Intel processor fine. Pull the one with the GUI. Don't get the one with no GUI. You will need the GUI. It's not very big. You could fit it on a CD. You could fit it on a mini CD, but nobody remembers what they are. What else is there to say here? Linux, the source code. If you find it in your repo, in your distributions repository, it might be old. You might want to pull the source and compile it yourself. And if you are reasonably au fait with Linux, that shouldn't give you too much difficulty. The trouble with the compilation comes if your distribution requires Qt5. Elmer is still, I think, on Qt4, and linking it, if you build it with the Qt from your distribution, then you will end up with link problems. So you need to get a copy of Qt4 and build it against that. So there's quite a bit of fiddling to do. Well, not quite a bit, some. I managed it, so it's not that hard. I'm a bear, for God's sake. All the bears are bear instruments are bears. There's not much in the way of help. If you need help, the best place to go looking is the forum. So this one. If you go looking here, elmerfem.org/forum, that's where help comes from. Help doesn't really come from YouTube that much, which is why I thought I'd do some videos. There are some cool use cases on YouTube, but there's not much in the way of this is how you click this, then click that, then click the next. Walkthroughs, that's what I mean. Not much in the way of walkthroughs. Righty, so Elmer comes from here. But this is not the official Elmer homepage. This is. It looks very similar. I can't really even work out what the difference is. You can obtain it from here as well. There's some interesting white papers and documentation. Documentation, when you get to look at it, I think I've got some open here. Here we go. Elmer FEM. Go away. Not that one. Looking for proper blah 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 blah. There we go. Models manual. So this is what the models manual looks like. If you end up getting help on the forum, there's a very good chance that this chap, whose name I will not incorrectly pronounce and embarrass myself, obviously I can manage Peter, may well be the person who answers you. If you use Elmer, then you owe him some thanks. He's put a lot of his life into it, I think. So you will find the manual looks a bit like console manuals if you use console, in the sense that you get theory, and then you get talk about boundary conditions, and then you get, in the case of Elmer, keywords that you use to explain the model setup to the solver. There is also a solver manual that tells you how the solver works and how you can write your own solvers and so on and so forth, but we needn't get into that at the moment. Alrighty, so you've obtained Elmer, and it comes with a GUI, and the GUI looks like this. It's superficially somewhat similar setup to ANSYS Maxwell or to COMSOL, in the sense that you have a what should we call this? A CAD window, I guess. This is a 2D thing which we will end up modelling, and I can move it, but it's a 2D. Whoops, I've got email. It's a sheet, so yeah, that's a 2D problem, and it's already meshed, obviously. Now, how do I make that go back and look nice? view. Should be reset view or something like that. Too sad. Reset model view, there we go. It was red because I had stuff selected. So we have a set of bodies, including some coils and a core and some air, coils, core, air gap. And we've got some equations, some boundary conditions as well. That's the outer boundary. All the energy has to stay within the boundaries. The most complete way of defining it. This is all the other boundaries that I haven't set anything on. Equations cover this domain, and this equation is Magneto Dynamics 2D, which is in the manual, and it's the manual pages that I just had up. And if you double click it, you get boxes where you can tell it stuff and things, including whether it's active or not, how important it is to execute this particular solver and where it applies, and you can edit the settings. And if you are familiar with some of the other packages, then if I go into linear system solution, things like mumps and BiCGStab and that sort of thing will be familiar. They're not words, but you know what I mean. That sort of thing. So that's how you do the kind of setup. And obviously we have other equations we can add. I bet if we went all the way to the left, so advection diffusion, electrostatics, that sort of thing, heat flow. This is oscillators, but I think it's not too sure what domain that applies to. You can have a Helmholtz oscillator in lots of different domains. Anyway, there we are. So that's what that looks like. We can set up materials. You have all the usual material properties, and the material properties that are required depend on the solver you're using. So if you're solving magnetodynamics, then you'd have reluctivity, which is 1 over permeability, I think. And you'd have conductivity, and you might set a BH curve. And there's a material library, which is not terribly extensive, but you can add your own things if you need to. Whereas if you are modelling in electrostatics, you want to have the permittivity. If you're dealing with heat flow, you need to have the conductivity and emissivity, and presuming it's radiating, that is, and so on and so forth. So that's how you would set up your problem like that. Body forces, these are where you will set what the stimulus to your model is. So in the case of magnetodynamics, you set the current density, and then the solver. Sorry, my laptop is sat on my leg, and the recording of video makes it so hot it burns my leg. Might be time for a new computer. It's used the current density to calculate the magnetic vector potential, and if you want things like the B field, then you take the curl of that across the domain. So the current density is the thing you set. If you need to set up a coil, there are a couple of different ways of doing that, and I will discuss them later. So for now, we will be dealing with current densities, which is, you might argue, it's not a terribly helpful thing to do, because the first question you get is, how much current is created the current density? Well, we can deal with that in a bit. I just want to get through the workflow, and then in a later video we'll build it up to something a bit more spectacular. So there's obviously current goes in, current density goes in the page, current density comes out of the page, or possibly the other way around, doesn't really matter. Initial conditions, you can set them here. All you'd be setting is the initial magnetic vector potential is 0. Outer boundary is infinite boundary condition, and that equates to a Robin boundary, roughly speaking. And you can find that in the model manual. So that's what it looks like. To the business of importing the mesh and all that, we will do later. This is just to say hello to it, more or less. When you are finished with the setup in the GUI, you can generate a CIF file. And it's the CIF file that actually tells the solver what to do. and all it has is everything we just discussed, all laid out in words, and it's text input to the solver. So that's the point of the GUI, is to generate this, and then when you run the solver will look at this and decide what to do with it. You can edit this directly, and as the problems become a little bit more involved, it will become necessary to start tinkering with the CIF file. So we can start out with the GUI, but before we get to the solving, we have to manually start making adjustments or adding things into the solver, the CIF file, which the GUI doesn't necessarily support easily. As I said, there is a barrier to entry, about a time barrier to entry. So we've got Elmer GUI. There's Elmer. The dog is chasing a fly in the kitchen. He's not going to catch it. Before we can get here though, we need to have actually meshed it. And to mesh it, we will use a mixture of Elmer Mesh and Salome. Salome is entirely separate software created by Open Cascade. What's the Open Cascade Foundation? Not sure. Let's go back to the internet. Salome is an open source software that provides generic pre- and post-processing platform for numericals. A generic pre- and post-processing platform for numerical simulation. So that's what it is. What does it look like? It looks like this. So this is the case that we just looked at in Elmer GUI solved. We will return to this. So this is actually in Paraview. You may or may not be aware of Paraview. It's an open source visualization package which is built into Salome. But if we go back to the beginning, we can see a geometry. So if you like console, this will look very familiar. Different shades of grey, and when you put your mouse over them, they change colour, and you can use the mouse wheel to determine the depth into the 3D that you're choosing. And that's there isn't any of that 3Dness here. This is a 2D problem. Oh, sorry. This is a 2D problem. So it's the same sheet problem that we had earlier. Who did that? Wasn't me. There we go. Nice upside down. Come on, come the right way up. Nope. 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 Yes. Good. Try on iteration. There is also a meshed version, and then there is the solution, because you only get the solution once you actually run it. So we will go through in the next video how to generate the geometry, and then how to do the meshing in another video, and then how to do the solving and so forth. But just to give you a snapshot of what's going to happen, presuming I find the time. So having meshed it, so there's these different. If you like Freecad has a very similar arrangement. It's a different. I suppose to some extent Eclipse does as well. You can choose how it displays itself to you. You have, like a CAD program, things down here. These are actually lines. They're points. Then we get into boxes and faces, and eventually we get into mesh. Doing 2D in Salome is actually quite laborious and time consuming. It's much quicker to do 3D drawings. If I was doing something in anger, as in I was on the clock and I was charging somebody for it, I'd probably draw this out in Creo and then import it as a DXF or a step file, and then mesh it in Salome and push it to Elmer that way, because it's a lot quicker. But to keep it as fewer programs as possible and to demonstrate how you do 2D in Salome, if you wanted to, we will do it in Salome. So having made the mesh, you would export the mesh, and you need a little bit of a DOSBox. Do we still call it a DOSBox? I do. I suppose you could call it a console. If I was in Linux, I'd call it a console. But this is a DOS box, even though there's no DOS. And you run a command, which is Elmer grid, and then you need a couple of numbers that tells it what your input file type is and what it's supposed to do with it. And then you give it the file name that you exported from Salome, and it changes it from a UMV, which is Universal Grid Mesh format, into Elmer's internal format, which you can load with Elmer GUI, and then you do all your bodies, and you assign the body's already created. It's a little bit wrong there. The bodies already exist. You apply the equations and the body forces and the materials and so on and so forth, and then you create the CIF file and then you solve it. And then you look at Paraview. So that's the overall scheme. And this is the problem we'll solve, which, if we go back to the geometry, is a coil which goes into the page here and comes out of the page there, or the other way around, doesn't really matter how you think about it. A core which is made of N87, and a box which is filled with air. And we will attempt to compute the magnetic flux density in the core and the magnetic field in the gap. I mean, we'll get the magnetic field everywhere, but the magnetic field in the gap, H field lives mostly here, which is why people say that the energy in the inductor is stored in the gap, because the energy is in the H field, or the potential for energy release is through to the collapse of the H field. So there we are, even though it's not really possible for the air to store energy. Okay, hopefully that's a reasonably clear walkthrough of what will be coming. I don't know if I've missed anything. Let's see. We discussed Salome, we discussed there was geometry, and that we would mesh it, and that we would later use it to view the result. We said that having meshed it, we export it, and that we use Elmer Mesh. I may not have actually used the word Elmer Mesh. I go right down to the bottom and press up. Elmer Grid. Elmer Grid, not Elmer Mesh. Mesh, grid. What are you going to do? Elmer Grid, to create the grid in the format that Elmer wants to have it. That we will use Elmer GUI to set up our problem in terms of the stimulus and the equations that apply, the boundary conditions and so on and so forth, and that we will generate a CIF file, and that we will use the solver, or when I say use the solver, I mean you click run, start solver, to solve it. And we can set up the solver here as well, or we can edit the CIF file, and if the problems become a little bit more complicated, we'll probably have to do that. And that we will go back to Salome. Oh dear, the dog's gone. To use Paraview to view the results. Righty, I'm going to go and answer the door. Bye.